Applications of linear equations. So what we're going to do is we're going to look at a verbal expression and we're going to write how we would write that in math terms. So we'll make a couple columns. Write the verbal expression on this side and the math expression on the other side. Okay, the first verbal expression is the sum of a number and 7. The sum of a number and 7. So the way that we would translate that into math terms, the sum means addition. So we're adding some number and 7. So when we don't know the value of a number, we use a variable. The most common variable we use is x. So we can write this as x plus 7. And because addition is commutative, which means you can add in whatever order you want to, we could also write this as 7 plus x. So either one of these expressions accurately represents the verbal expression, the sum of a number and 7. Okay, the next verbal expression is 6 more than a number. 6 more than a number. The math expression for this, 6 more than a number. So we take a number and we add 6. Because this is addition, we can also write this as 6 plus x. So x plus 6 or 6 plus x. Okay, I'm going to go ahead and write a few of the verbal expressions, give you guys some time to copy it, and then we'll go back and look at the math expressions after we get a few down. So the next one is 3 plus a number. 3 plus a number. Then we have 24 added to a number. 24 added to a number. Next, a number increased by 5. A number increased by 5. And we'll do one more, the sum of 2 numbers. The sum of 2 numbers. Okay, so let's go back and look at the math expressions for these verbal expressions we just wrote. 3 plus a number. Hopefully that one's pretty simple. 3 plus a number. When we don't know what the number is, we use a variable. So we'll write 3 plus x. And because this is addition, we can also write it as x plus 3. Next one, 24 added to a number. 24 plus x, or x plus 24. The next one, a number increased by 5. So some number x increased by 5, so that's plus 5. Or we could write it as 5 plus x. The sum of two numbers, we don't know either of the numbers' values, so we use variables, and we're adding two numbers, so we'll just say x plus y. Or technically, we could write this as y plus x. Or you could use any variable you want, a plus b, whatever you want. Okay, that takes care of all of the different ways addition can be verbalized. So anytime you see these numbers, the sum, 6 more, plus obviously should be a dead giveaway to use addition. Added should also be pretty easy to figure out. Increased and sum again. All of those mean addition. All right, let's look at a few more. 2 less than a number. Two less than a number. The next one is 12 minus a number. 12 minus a number. A number decreased by 12. A number decreased by 12. A number subtracted from 10. A number subtracted from 10. We have from a number subtract 10. From a number subtract 10. Next one, the difference between two numbers. The difference between two numbers. Okay, let's write the math expressions for those 6 that we just wrote. Okay, 2 less than a number. So we're starting with a number that we don't know what it is. We'll call it x. 2 less than that number would be x minus 2. So subtracting 2 from some number. Okay, order is very important when you're looking at subtraction. Order didn't matter with addition because you can add numbers in whatever order and still get the same thing. With subtraction, it's different. 4 minus 2 is different than 2 minus 4. So be very careful with the order you write these in when it involves subtraction. Like the next one, 12 minus a number, we write it just as it's written, 12 minus a number, which we're calling x. a number decreased by 12. So start with a number, x, and we're decreasing it by 12, so subtract 12. A number subtracted from 10. So we start with 10 and we subtract a number subtracted from 10. So we get 10 minus x. From a number, subtract 10. So we're starting with x. From a number, subtract 10. X minus 10. Finally, the difference between two numbers, that would be x minus y. All right, let's look at a few more verbal expressions. Got 16 times a number. 16 times a number. Next one, a number multiplied by 6. A number multiplied by 6. Two-thirds of a number is the next one. Two-thirds of a number. Three-fourths as much as a number. Three-fourths as much as a number. Twice as much as a number. Twice as much as a number. And we'll do one more, the product of two numbers. The product of two numbers. Okay, let's go back and write the math expressions for these. 16 times a number. Times, you know, means multiplication. So 16 times x, we would write as 16x. 16 times a number. A number multiplied by 6. So a number x multiplied by 6. So x times 6, which again, we would just write as 6x. It's not wrong if you write it x times 6. But when you have a variable involved, it's just easier to write it this way, 6x. Two-thirds of a number. Anytime you see the word of in a problem, Of means multiplication. So 2/3 of a number means you're multiplying 2/3 times a number. So 2/3 x. Okay, 3/4 as much as a number. 3/4 as much as a number also means multiplication. And 3/4 kind of throws me off. Sometimes you're more likely to hear half of a number. So when you hear half of a number, you take that number and you divide by 2, which is the same as multiplying by 1/2. So 3/4 as much as a number means you're taking that number and multiplying it by 3/4. So 3/4 x. So as much as is also going to lead you to multiplication. Those words as much as. So the next one, twice as much as a number, means you're taking that number multiplying by 2. So 2x. The product of two numbers, the product is the result of multiplication. So the product of two numbers would be x times y, or a times b, or h times k, or whatever your variables are, or whatever your numbers are. Okay, we got 3 more like this. The quotient of 8 and a number. Quotient of 8 and a number. A number divided by 13. And the last one, the ratio of two numbers. The ratio of two numbers. Okay, let's look at the math expressions for these. The quotient of 8 and a number. A quotient is the result of division. So we're going to divide 8 and a number. So whatever number comes first is being divided by whatever number comes second. So we write this as 8 over x. Again, it's not wrong to write this as 8 divided by x. But in this class and any upper level math, you're never going to write division like this. You'll always write it as a fraction. Next one, a number divided by 13. So this time x is in the numerator and we're dividing by 13. So x over 13. Last one, the ratio of two numbers. Ratio means you're dividing two numbers. So we'll write it x over y. So this ratio would be the ratio of x and y. If it asks you to write the ratio of y and x, then the y would be in the numerator. Whatever number comes first is going to be in the numerator. Okay, let's write a little note here. We want to make sure that we know it is very important to write numbers in the right order when using subtraction and division. Very important to write numbers in the right order when using subtraction and division. So with addition and multiplication, you can do that in any order and get the same result. But with subtraction and division, the order matters. So be very careful. Look at the words really carefully before you write your mathematical expressions. Okay. We are going to look at some longer sentences now. Instead of just these verbal expressions, we're going to look at some written sentences, and we're going to translate those into actual equations. So instead of just expressions like this, we're going to look at how to write an equation based off of words that you're given. So I'm going to go ahead and flip to the other side of my page. So we're going to have a verbal sentence, and we're going to write an equation. Okay, first sentence. Twice a number decreased by 3 is 42. Twice a number decreased by 3 is 42. So twice a number, we wrote that one on the front. That just means you're taking 2 and you're multiplying it by a number, which we're calling x because we don't know its value. So twice a number decreased by 3, that means we're subtracting 3 from that, is 42. Is going to be your equals. That word is means equals 42, or it gets translated as an equals. So our equation for this sentence is 2x minus 3 equals 42. The next sentence, the product of a number and 12 the product of a number and 12 decreased by 7 is 105. The product of a number and 12 decreased by 7 is 105. So the product of a number and 12, that would be 12x, decreased by 7, so minus 7, is 105. So equals 105. Okay, the next sentence, the quotient of a number and the number plus 4 is 28. The quotient of a number and the number plus 4 is 28. Okay, the quotient of a number and the number plus 4 would be x over x plus 4. So quotient means division. Whatever number is listed first goes in the numerator. So the quotient of a number, x, goes in the numerator, and the number plus 4. So that same number, x plus 4, is what goes in the denominator. And that is 28, so equals 28. The next sentence, the quotient of a number and 4 plus the number is 10. The quotient of a number and 4 plus the number is 10. Okay, in this one, we've got to watch where the commas are. So the quotient of a number and 4, pause. Let's write that first. The quotient of a number and 4 would be x over 4. Then we're done with that quotient. Then we have plus the number, so plus x is 10. So the commas are what makes the difference between this and this. This plus x does not go in the denominator with the 4 because it tells us the quotient is just between the number and 4. Then there's a comma. That means we're done with the quotient. We're adding 10 outside of the quotient. So this is incorrect. All right, next one, the sum of a number and 6. The sum of a number and 6 is 28. The sum of a number and 6 is 28. Sum means addition, so we're adding a number plus 6. X plus 6 is 28, so equals 28. Two more. The product of a number and 7. The product of a number and 7 is twice the number plus 12. The product of a number and 7 is twice the number plus 12. The product of a number and 7, that would be written as 7x, is, so equals, twice the number, so 2x, plus 12. 7x equals 2x plus 12. So it tells us that the number on the right side, the unknown number, is the same as the one from the left side because it says the product of a number and 7 is twice the number. So the same number that we just used, not twice a number. So it matters that we use the same variable on both sides. One more. The quotient of a number and 6 quotient of a number and 6 added to twice the number is 7. The quotient of a number and 6 added to twice the number is 7. Okay, the quotient of a number and 6 would be x over 6. X is in the numerator because the number was mentioned first, 6 was mentioned second. And that is added to, so plus twice the number, which is 2x, is 7, so equals 7. So again, we're using the same variable throughout because it says the quotient of a number, it could be any number, which means we could use any variable. We could use X, we could use Y, we could use A, B, whatever letter of the alphabet you want. But as soon as we choose that letter, that's what we stick with when it says added to twice the number. So the number that you chose, the variable that you chose to use, you use it throughout the equation. So now we're going to look at what it takes to solve a word problem, an applied problem. So we got some steps that we're going to write down first. So I'm going to paraphrase these steps just because we've already written quite a bit today. Steps for solving an applied problem. First step might be obvious, read the problem. Read it, reread it, however many times you have to until you understand what's being given and what you're being asked to find. Step 2, assign a variable. Assign a variable. So whatever you're going to be asked to find, that's your unknown value. You're going to assign a variable to that unknown. You can draw pictures, diagrams, a table, whatever you need to make sure you understand what this variable is representing. Step 3, write an equation. So just like we did with the sentences at the top of this page, you're going to use your variable to write an equation based on the problem that you're given. Then step 4, solve the equation. So get the variable by itself so that you have a value that you can now assign to that variable. Last step is to check your answer. You don't necessarily have to plug your answer back into the equation and check it. I just mean check to make sure that your answer makes sense. So go back and reread the problem, make sure that your answer is a legitimate value for what is being asked. So if you're asked to find the distance between two things and you find a negative value, that doesn't make sense. It doesn't make sense for distance to be negative. So that would tell you that maybe you did something wrong. You can go back and check your work. Okay, let's work some problems. Example 1. Okay, the length of a rectangle is 1 centimeter more than twice the width. The length of a rectangle is 1 centimeter more than twice the width. The perimeter of the rectangle is 110 centimeters. Find the length and width of the rectangle. I'll give you guys a second to finish copying this. All right, first step, read the problem. So let's read. The length of a rectangle is 1 centimeter more than twice the width. The perimeter of the rectangle is 110 centimeters. Find the length and width of the rectangle. Okay, step 2, assign a variable. So we have two things that we're trying to find, length and width. So I'm saying L equals length, using a lowercase cursive L so that it doesn't look like a 1. And W equals width. So we've assigned our variables. Step 3, write an equation. So based on the problem, the length of a rectangle, which is L, is, so equals, 1 centimeter more than, so that's 1 plus twice the width, so 2W. L equals 1 plus 2W. Okay, but then it also tells us the perimeter of the rectangle is 110 centimeters. So how can we get the perimeter, we'll call that P, using length and width? If it's a rectangle, then we've got two sides, that would be called the length, plus two sides, that would be the width. So the perimeter, you're just adding all four sides together, but since it's a rectangle, we know that opposite sides are the same length, have the same measurement. So our perimeter can be written as 2L plus 2W. So when it tells us that the perimeter of the rectangle is 110 centimeters, we can say 2L plus 2W equals 110. And now we have a system of equations that we can solve. So we did this before Christmas break, solving systems of equations. This first equation is already solved for L. So I'm going to take this L in my second equation and replace it with 1 plus 2W because those are equal values. And that's how I'll be able to solve. So instead of L right here, instead of 2L, I have 2 times 1 plus 2W plus 2W equals 110. So all I did was take this equation, my second equation that I wrote, but instead of L, I plugged in what L is equal to, which is 1 plus 2W. Now we have an equation that only has one variable, so I should be able to solve for that variable. So get rid of the parentheses by distributing this 2. We get 2 plus 4W plus 2W equals 110. We can combine like terms. 4W plus 2W is 6W. Subtract 2 from both sides. We get 6W equals 108. And divide both sides by 6 to get W equals 18. Okay, but we weren't asked to just find the width. We were asked to find the length and width. So go back to the first equation we wrote, L equals 1 plus 2W. Now we're going to plug in what we know W is, which is 18. So L equals 1 plus 2 times 18. Well, 2 times 18 is 36, plus 1 is 37. All right, so those are our answers. The length is 37 centimeters. And the width is 18 centimeters. Can check our answer. If we look at the perimeter, we're told the perimeter is 110 centimeters. So that means 37 plus 37 plus 18 plus 18 should equal 110, and it does. Okay, let's look at another example. So this is example 2. Okay, I'm just going to write this problem, and then I'll give you guys a few minutes to copy it. Okay, take a second to copy all this down. Okay, let's read this problem. Two outstanding Major League pitchers in recent years, which I'm not sure when this problem was written because it mentions 2004. That's not very recent anymore, but it is what it is. Two pitchers, Randy Johnson and Johan Santana. In 2004, the two pitchers had a combined total of 555 strikeouts. Johnson had 25 more strikeouts than Santana. How many strikeouts did each player have? Okay, so we're looking for number of strikeouts each player has. Let's assign some variables. We'll say J equals number of strikeouts for Johnson. And S equals number of strikeouts for Santana. Okay, we've assigned our variables. Now let's write some equations, or some expressions at least. It tells us the two pitchers had a combined total of 555 strikeouts. So that means J plus S equaled 555. Also tells us Johnson had 25 more strikeouts than Santana. So if we take the number of strikeouts that Johnson has, that's equal to the number of strikeouts Santana had plus 25. Johnson had 24 more strikeouts than Santana. So you take the number that Santana had and you add 25, that's how many Johnson had. Okay, so we've got the same thing here as in example 1. We have a system of equations. We just need to solve the system. So we have this second equation is solved for J. So in the first equation, I'm going to replace J with what I know J is equal to, which is S plus 25. So instead of J plus S, I have S plus 25 plus S equals 555. So I just took the first equation, but I plugged in S plus 25 instead of J. Now I have an equation that only has S, so I should be able to solve for S. So I've got S plus S on the left side. We can combine those and say 2S plus 25 equals 555. This is a lot of 2's and S's and 5's. Subtract 25 from both sides. We get 2S equals 530. Divide both sides by 2. S equals 265, is that right? 530 divided by 2, yep, 265. Okay, so we have a value for one of our unknown variables. Now we need to find how many strikeouts Johnson had. So we go back up to the second equation in our system. J equals S plus 25. Well, we know S is 265, so J equals 265 plus 25. So J equals 290. So double check our answer. We were told that when you combine the total number of strikeouts, or when you combine both their number of strikeouts, the total number is 555. So just double check that 265 plus 290 equals 555, and it does. Okay, so our answer, Johnson had 290 strikeouts, and Santana had 265 strikeouts. The good rule to go by is if you're given your problem in sentences, you write your answer in a sentence as well. Especially because you have assigned specific variables to the unknowns, and whoever is grading your paper might not necessarily know what those variables mean. So if you just tell me J equals 290, I might think that that stands for Johan Santana. So you have to write your answer in a sentence and be specific about what your answers mean. Okay, we've got time for at least one more example. So this will be example 3. Okay, I'm going to write example 3 and then I'll give you guys some time to copy it. Okay, you guys copy example 3 down. Okay, let's read through this example. In 2002, there were 301 long-distance area codes in the United States, an increase of 250% over the number when the area code plan began in 1947. So the question is, How many area codes were there in 1947? So the unknown value is the number of area codes in 1947. We assign a variable to that. I'll just use A for area code. So A is going to represent the number of codes in 1947. Now we need to write our equation. So the number of area codes in 1947 is A. And there was an increase of 301, or sorry, there was an increase of 250%. So an increase means we're adding 250% of the number of codes that there were in 1947. So let me do some scratch work here. 250% of A, which represents the number of codes in 1947. 250% as a decimal is 2.5. Of means multiplication. So 250% of A can be written as 2.5A. So we start with A, which is the number of codes in 1947, then we add 2.5A to get the number of area codes that we had in 2002, which is 301. So this is number of codes in 1947 plus the increase. Erase my scratch work. Equals the number of codes in 2002. That's what we're doing in this equation. The number we started with plus the increase to get the number that we had in 2002. Okay, just the one equation this time. Now we can solve for A. So A plus 2.5A is 3.5A. Divide both sides by 3.5. $301 divided by 3.5 is 86. So our answer is the number of area codes in 1947 was 86. Okay, we'll stop right there. We still have a couple more examples, so we'll pick up with those two examples next time before I give you guys your practice problems.